Good morning, everyone. So we have seen already that once we are solving a continuous system, there are the two ways we have seen that the transfer element the transfer element formula transfer matrix formulation and spectral element formulation. So and we have also mentioned that both the thing can be interchangeably do. I mean, we can do both the thing interchangeably. So now let's see how we can able to do both the thing interchangeably, and what is the mathematical way how we can able to calculate, so that if we have one, we don't need to calculate the another from the scratch. Rather, we can just use it from the previous one. So let's go it for spectral to transfer and vice versa. Okay, so for giving that example, maybe let's consider the case of a let's consider the case of a beam. So this is like a beam. So here we are having W1 theta 1 W2 theta 2, that is always, and then we will have here this is V1 M1 V2 M2. Okay, so if you see this V1 M1 V2 M2, that is the orientation we are using for the spectral element formulation. That is we are using for the transfer matrix formulation. Transfer matrix formulation, because these orientation of the forcing parameters come automatically once you are solving the differential equation. And once you are doing the spectral element formulation, spectral element, it is coming like V1 M1 and it will be V2 M2. So here we can see that interestingly our V2 here and V2 here, maybe I can just call it like V2T and this is V2S. So V2S is equal to minus of V2T, and M1S is also minus of M1T. So that are the two differences only. Other two are exactly same. That is like V1 equal to V2 and M2 V1 equal to V1, V1S equal to V1T, and M1 M2S equal to M2T. They are exactly equal. They are not having any problem. So we have seen already that once we are having the spectral element matrix, then in that case we are having so in the spectral element form, once we are writing it in the spectral element form, once we are writing the forces in left hand side, that is V1S M1S V2S M2S, that will be equal to our spectral element matrix into W1 theta 1 W2 theta 2. I am just writing W1 theta 1 W2 theta 2 because they are same for both the cases. So I am not using any other subscripts. So that is just the same. So that is happening for the spectral element case. So here it is like you can say that S11, S12, S13, S14, like this way that full matrix is there. That's a full matrix like this. Okay, and transfer, how we are writing transfer, it is like transferring from one side to another side. So in that case we are having V1 transfer, or maybe we can just start like this way, W1 theta 1 V1T M1T equal to transfer matrix with W2 theta 2 V2T M2T. Okay, perfect. So now here what can we see? That once we have this, now we can think that, so this thing I can say d1 displacement 1 and this is displacement of 2. This is force of one node, this is force of two node. So I can just write it S F1 d1, this is S F2 F1 d2, this is S F2 d1, this is F2 d2. And once I am doing, this is my displacement of 1, this is my force of 1, this is my displacement of 2, this is my force of 2. So how we are writing it? So that is T d1 d2, T d1 f2, T f1 d2, T f1 f2. So that way we can able to write the full thing. So now from this equation, now if I change it, that f1 equal to S f1 d1 into d1 plus S f1 d2 into d2. I can able to write that, and my objective is to write it like d1 f1 in terms of d2 and f2. Okay, so what should I do? I should try to take the d1 and f1 in the left hand side and try to express all those things in the terms of f2. So first thing, maybe I should write f2. f2 will be df2 d1 d1 plus s f2 d2 d2. Okay, so if I try to write it, so from this equation what can I write? I can write d1 equal to s f2 d1 inverse of f2 minus s f2 d1 inverse into s f2 d2 d2, that I can able to write. Okay, and you can see that this full thing is expressed now in the terms of f2 and d2. Now if I substitute this one here and just try to write f1, what can I get? f1 equal to s f1 d1 into s f2 d1 inverse f2 minus s f2 d1 inverse into s f2 d2 into d2. So s f1 d1 into s f2 d1 inverse f2 minus s f1 d1 s f2 d1 inverse s f2 d2 into d2. That we can able to get. And now if I write the full thing in the matrix form, what will I get? I will have d1 f1, then full thing in the matrix d2 f2. Oh, I can able to write it. So the first term, so that will be maybe my first, so that will be my second term, that is t d1 f2. This term will be t with the plus and minus, so that will be t d1 d2. This term will be t f1 f2, and yes, with a plus and the minus sign here, this term will be t f1 d2. So we can just plug those terms here and we can able to get what is the transfer matrix. Here one point we have to remember, that once we are substituting, this thing we have to take in mind. So once we are doing it, we should change that sign. Don't forget that thing. Okay, so like this way we can easily able to convert from dynamic stiffness matrix to the transfer matrix, or vice versa. If you have one, you can also get the another one. That's the way how we can able to do that. so we have seen already that how we can able to do for a finite beam, how we can able to get the stiffness matrix and all those. So now let's check how we can able to get the stiffness matrix for a semi-infinite beam. So that's the interesting thing, that is semi-infinite beam. So semi-infinite beam. Semi-infinite beam or maybe bar, whatever. So that is something like a member where we can see that like its one end is actually going to infinity. So and another end may be fixed or something, so it's like a infinitely long, or maybe we are giving excitation at some point and it is going like a infinitely long. So how we can able to simulate that type of bar or beam? So there actually stiffness element based approach provides a very nice way of solving that thing. How we can able to do that? So let's see. So first of all, like maybe if we are assuming this is a Euler-Bernoulli beam, we can able to write EI del 4 W del x4 plus rho e into del 2W del T2, that is equal to 0. That's my Euler-Bernoulli basic equation of motion. And we all know that we can assume W of x comma t equal to phi of x into q of t. That is like a summation of I equal to I equal to 1 to n. That we all know. That this way we can able to write it. And once we can able to write it, we can again substitute that full thing here. So ei summation of phi I x fourth order x into q I of t plus rho e summation of I equal to 1 to n I equal to 1 to n phi I x into q I double dot t, that will be equal to 0. Okay, so now once we have this, then we have also seen that once we are writing this type of way, that it is valid for all the modes. So we can able to write it ei summation of phi I for x into qit plus rho a into phi I x into qi double dot t equal to 0. Now for harmonic solution, we can say that qi of t equal to e to the power of I omega t or maybe j omega t. So that means qi double dot t should be equal to minus omega square e to the power of j omega t. So therefore, if I substitute it, ei fourth order of x into plus rho a minus omega I square into phi I x, that is equal to 0. So if this is the equation of motion, then we can able to write it so we have this type, this way it is coming. Now once we have that, so from here we can able to write it that this one equal to a1 into e to the power of lambda x. So a into e to the power of lambda x, so that way if we are substituting it, so that lambda to the power 4 minus rho e omega squared divided by ei, that will be equal to 0. And so the fourth value of, so we will get the fourth value of lambda, and for each value of lambda if we can substitute, so we will get it. So we can get phi of x, that will be equal to a1 e to the power of lambda 1x plus a2 e to the power of lambda 2x plus a3 e to the power of lambda 3x plus a4 e to the power of lambda 4x. That way we can get the solution. Now if you see, this is my phi. So what is my rotation? So rotation will be theta of x, that will be nothing but del w del x. So del w del x means it will become phi dash x. Phi dash x, and then with the qy, that is dependent on time, so we don't need to be worried with that. So this will become phi dash x, so that will be a1 lambda 1 e to the power lambda 1 x plus a2 lambda 2 e to the power of lambda 2x plus a3 lambda 3 e to the power of lambda 3x plus a4 lambda 4 e to the power of lambda 4x. Like this we will get. So now once we will write the sides, like for example phi of 0, phi dash of 0, phi of L, and phi dash of L, we can able to get that full thing, and we will a1 a2 a3 a4 we can able to get. So these all are my degree of freedom, D, and these are my unknown, A. So here we will just substitute the values, like this one will become a to the power lambda 0 like this way, and then here it will become lambda 1 into e to the power of lambda 1 0, and then we have to substitute lambda 1 L, lambda 2 L, like this way we have to substitute. So we will get a definite matrix. So maybe I just call it a D to A, so that may be like a D matrix, not D matrix, maybe let's just call it K matrix. Okay, I wrote it like that way. Then okay, now how we can able to get the shape functions? So shape functions can be obtained like once you have like a w of, or maybe you are just try to get that phi of x. So once we are writing that phi of x not in terms of a1 a2 a3 but in terms of d1, means the displacement forms, like on the both the side, like phi 0 phi l phi dash 0 phi l, so phi dash l, then it will become your like a shape function. So I am trying to writing it. So my objective is to write the phi x. So phi x I can write it like e to the power lambda 1 x, e to the power lambda 2 x, e to the power lambda 3 x, e to the power lambda 4 x with a1 a2 a3 a4. Okay, this is already I got it, so I can write it k inverse of d. So if I just do, then it will become e to the power lambda 1 x, e to the power lambda 2 x, e to the power lambda 3 x, e to the power lambda 4 x, then k inverse times t. So this complete thing will give me a matrix for the shape function. So if you see here that have a 1 cross 4 number of element, and this is 4 cross 4, so the resultant will be 1 cross 4. So that means this has a single row with 4 columns, and each of them are the shape function for first shape function, second shape function, third shape function, fourth shape function. So like this way we can able to get the shape functions. So that is for the normal beam. And now if we are going ahead from here, then so what eventually will happen, we can see that phi x we can able to write it in terms of like something like in1 x into in1 x into phi 0 plus into x into phi dash 0 plus in 3x into phi L plus in 4x into phi dash L. That way we can able to write the phi, and these are, so here in 1, in 2, in 3, in 4 are the shape functions for that. And these shape functions are frequency dependent. Why? Because if you see that this shape functions has a term e to the power lambda 1x, e to the power lambda 2x, lambda 3x, and if you see that lambda is dependent on omega, so they are frequency dependent, no doubt on that. So this way, in that spectral element formulation, we will have the shape function, frequency dependent shape functions, okay, by which we can able to express the complete field, displacement field, velocity, rotational field, those things we can able to represent by that. Okay, so we will have that. Now next one we are coming. So that is one of the way how we can able to get the shape functions also, and then we can able to express it in the form of the equations, and also so we can able to get that. And we have already discussed that once we go like this way, how we can able to get the transfer matrix, and we can how we can able to represent it in form of transfer matrix and spectral element, that we have also discussed. Now if you see that from equation number 1 we can also able to express it in the weak form. So just let me write the equation number 1, that is summation of I equal to 1 to n phi I to the power 4x qi t plus rho e summation of I equal to 1 to n phi I x into qi double dot t, that will be equal to 0. Now we are doing the integration, we are performing the integration from 0 to L ei, and we are try to multiply this with phi j. So phi j of x, we are multiplying the full equation over the term that we are actually doing. Okay, so phi of j we are pre-multiplying. Now once we are doing that, what is happening? So that is basically we are doing the weighted residual. So we try to minimizing the error and try to estimating that. So ei integral 0 to L summation phi jx into phi I to the 4x dx qit plus rho a 0 to L summation I equal to 1 to n phi jx into phi I x qi double dot t dx, that is equal to 0. So we can take that summation outside and we can write it 0 to L phi jx into double fourth order x dx into qit plus rho a summation I equal to 1 to n integral 0 to L phi jx phi ix dx into qi double dot t, that is equal to 0. So from here, important point is that we can write it in the matrix form, where q1 double dot, q2 double dot, q3 double dot, q4 double dot all are varying with q1, q2, q3, q4, that will come something. So here we can see that this portion will coming as like a diagonal, because other terms mostly will be 0, because once we are putting the phi, and if the phi, like if phi of x are orthogonal, then this will be a diagonal stiffness, I mean the diagonal matrix, and other one, this term will be coming here, and that will be a populated matrix. So that will act like a mass matrix, act like a stiffness matrix, and we can able to get the solution out of it. Now here, some other way also this can be possible. Like here, if you see, we have one is in the like 0th order derivative and another is in the 4th order derivative. So often we can take this part only, we can take this part only and we can do the integration by parts. So if we do the integration by parts 2 times, then what will happen? The first integration by parts will make this, and second integration by parts will make this. So here we can see that both the order of the differential will become similar. So that sometimes gives like a very nice symmetric type of thing we can able to get, and we can able to solve that. So, and this way, once you do the 2 times integration by parts and rewrite the full thing from the weak form solution, because this form of solution is the weak form solution. So from here we can actually able to say that we are going means once we are implementing this step also, then that become the finite element. Okay, so but here the difference is where with the normal standard finite element is that we are using a shape function which are continuous throughout. I mean, which are continuous and which are expressing the field in a much better manner. So that, and we don't need to do any discretization. Here these terms are not discretized in the space, they are discretized, or they are the modal superposition actually. So they are the different modes, so we are coupling all those modes together to get the solution. Okay, so this way this thing can be thought of, and we can get the matrices. Now if I come back to from where the discussion started, that we were actually we envisioned to obtain the stiffness matrix for the infinite element. So in case of the infinite element, we can write the displacement field as like phi of x will be equal to a1 e to the power of lambda 1 x okay, a1 e to the power of lambda x plus a2 into e to the power of lambda l minus x plus a3 e to the power of I lambda x plus a4 e to the power of I lambda l minus x. So these are the 4 functions we can get, and if we are, so this is that way. Now if it is the infinitely end, then we can ignore the wave coming from these two. So that is the normal one. So that is the normal one, the complete one. We had, if you see, one is going, so that may be looking little bit odd, but don't get out it. You can see that this is e to the power of lambda l into e to the power of minus lambda x. E to the power of I lambda x, a4 e to the power of I lambda l into e to the power of minus I lambda x. So that is nothing, means if you just multiply these two, it will be also become like something whatever we are writing at the beginning, because previously we got the lambda equation and that has the fourth order equation with omega square and some constant term. So if you do it, lambda will be like root omega something with root omega, means that something maybe s cube, maybe if I just write it. So that will be s omega s root omega minus s root omega is root omega and minus is root omega. So you see, I take all the things, I am not removing anything, I just put that two things. So here we can say that these two terms, like these two terms highlighted in the red, are actually representing the waves coming from the right hand side. Now if it is like infinitely long, then that two contribution will no longer be there, and we can then able to write our matrix for the infinite case. is like this into lambda x plus a3 into e to the power of I lambda x only. So once we write this, we can write whatever is the theta. Theta will be nothing but derivative of it. So I will get it e to the power of lambda e to the power of lambda x plus a3 iq e to the power of I lambda x. We'll have the theta in this way. So like this way we can able to get the solutions. And once we have this theta and this, so we can able to substitute it also. Like for example, if one side is like suppose you have a boundary condition at one side, so that is like a w of 0 and theta of 0. So w of 0 means that is phi of 0. So what can we substitute? We can substitute a1 into e to the power of lambda 0 plus a3 e to the power of lambda 0. So that means this is nothing but a1 plus a3, and this is theta, that is phi dash 0. That means a1 lambda e to the power of lambda 0 plus a3 lambda e to the power of lambda 0. That means that will be I. a1 lambda plus I a3 lambda, that will be something. So if we have those values, we can able to recalculate. So if you see, like you may have these values. So this is your D matrix. So you can just plug all those things here, lambda, I lambda with a1 and a3. So that is your A matrix, and this is maybe your K matrix. So what can you say? We can say that my A will be a1, a3 will be nothing but K inverse of your D. Okay. Now if you substitute that, what is your phi of x? That will be a1. Means a1 you will already get the value in terms of D. So you will just do it like e to the power of lambda x into e to the power of I lambda x into the inverse of K with D. So that will be your direct displacement field. So by this way you can easily able to obtain the displacement field and associated like a rotational field for the case of the semi-infinite beams. Any question or confusion up to this stage? Okay, if there is no confusion, we may close this discussion here. Thank you very much.